Good morning. I am glad to have you here. I hope your Thanksgiving was awesome. Let's finish out this term. So, got two announcements before we start relating to what's happening this week. I want to make sure you know. For your lab time this week, all right, there are basically three things that you need to bring, all right? And those three things are problem set number 6, all right? We'll talk about it. We'll take the last quiz number 6. Be good to go in that department. Also bring your lab notebook and a printed copy of the hydrogen spectrum lab. The lab notebook is, I'll collect them at the beginning of lab, so not the recitation, but the lab. I'll look them over and I'll return them to you and stuff. That will be due then at the time of your lab. If you're missing any stamps, you've got to get them from me during my office hours. I have office hours like right after class right now. I won't give out any stamps during the lab time this week. Also, make sure you bring a printed copy of the hydrogen spectrum lab. You'll actually fill that out and you'll turn it in before you leave, so there's nothing to type or anything like that. You also don't have to put any notes in the lab notebook for the hydrogen spectrum lab. So make sure you bring those three things whenever your lab time is this week, and that'll be awesome. The other announcement I wanted to make is that if you are trying to do the exam 2 extra credit, the time that it's due is a little strange. It's Wednesday at 1:10. So just realize that you can turn it in up to that time. It's mostly for Thursday mornings group. You can't turn the exam extra credit in Thursday morning. You have to do it by Wednesday at 1:10. Any questions on that kind of stuff?
That's this Wednesday, yeah.
Yeah, that's right. That's right. All right. We're going to finish off talking about new lecture material today, so it's kind of exciting. The first thing we're going to look at is how to make an ion when it comes to electron configurations. An anion is a negatively charged ion. So for example, phosphide, P-3, is an example of an anion. It has a negative charge. And to go from phosphorus to phosphide, you add 3 electrons. And adding electrons is the same as we did when we filled in the electron configurations earlier. You just put them in the lowest unoccupied spot. So phosphorus has a 1s2, 2s2, 2p6, 3s2, 3p3 configuration. You could abbreviate that as a neon core, 3s2, 3p3, and that would be fine. But if you want to have 3 extra electrons, they just go in the lowest unoccupied space. So there's 3 spots there for 3p. P's can hold up to 6. So that would be then a 3p6 configuration. So making a negative ion, you just put the electrons in the lowest unoccupied spot, all right? You don't go to the higher ones, you just go to the lower ones. And a lot of times, not all the times, but a lot of times, the final product will look something like a noble gas. And we'll talk about that more in the problem set this week. A cation is a positively charged ion. So in a cation, you'll take away electrons. So for example, there is a phosphorus 3+ ion. It's rare, but it does happen. And to make phosphorus 3+ from phosphorus, you have to remove 3 electrons. And the electrons, they come out in a way which is really highest N first, followed by highest N plus L. I'll talk about that. Now, as a quick review, because you probably didn't think about chemistry over the break, and I don't blame you, trust me, but anyway, the 3 numbers right there, those are the N numbers, all right? So for 2s, N would be 2, 4d, N would be 4, stuff like that. And the electrons come out of the highest N first, followed by highest N plus L. So here we have 3s and 3p. They're both n equals 3. So this is like a tie where you take electrons out. Highest n plus L basically in a nutshell means the last electrons in are the first electrons out. So for in this case we would add the 3s first, then the 3p. So if we're going to remove 3 electrons, you take them from the 3p electron orbital. So neon 3s2 would be the electron configuration for the 3+ ion.
Does it have those empty boxes? Is it necessary?
No, you could also, Joseph, just write it as 1s2, 2s2, 2p6, 3s2, which would be awesome. So, yeah.
Lithium or sodium?
Correct. This would be a neon 3s2 configuration. Yeah, that helps with figuring out magnetism. So notice that in both of these cases, what was left were all diamagnetic configurations. Yeah.
So, is there any case where the S's would be removed instead of the P's, or is that always true?
We'll come back to this in a little bit, but the highest n rame is the part to focus on, all right? So in this problem, 3 and 3, we had like a tie, all right? So we went to the highest n plus L, the last one's in or first one's out. Highest n will definitely make a factor here in a little bit, especially with the transition metals, okay? So hold that thought. Okay. So let's say that we wanted to figure out which of these ions was a 1s2, 2s2, 2p6 configuration, all right? And we got 4 different choices there. So what you can do then is literally go to the periodic table and remove or add electrons as appropriate. So sodium is number 11. 3s1 is the outermost configuration of sodium. And if you take away an electron to make sodium plus 1, a 3s1 electron would be removed. Sodium ion would have a 1s2, 2s2, 2p6 configuration. So that one is this one right here. So you might be tempted then to push A, and if you do, it's okay. But let's look at the next one just to make sure. And oxygen is a 1s2, 2s2, 2p4. 2p1 starts at boron. P2, P3, oxygen would be a 2p4. But we need to add 2 electrons to make oxide. So those extra electrons are going to go in the unoccupied spots. So the first electron would be a 2p5, and the next electron would be a 2p6. Oxide also has 1s2, 2s2, 2p6. And that is the configuration for neon. If you do the magnesium, it's the same thing. Lo and behold, all of those are the neon configuration. All of them are 1s2, 2s2, 2p6. And once in a while in this class, I babbled a lot. Oops, brought that fella. Once in a while I babbled about noble gases being the cool kids in the back of the bus. Well, here they are. All of the atoms want to be like the noble gases, all right? So sodium is always +1. It doesn't need a Roman numeral. All these things we talked about this quarter. That's because neon configuration, very, very stable. Oxygen, always oxide, never -1, -3 and stuff like that under normal conditions. Cool kids in the back of the bus. It wants to be like neon. Magnesium, always +2, is +2 because it's like neon. We're going to see how the noble gas configuration is an extra level of stability that the normal ones sometimes don't see. Any questions?
So electron configuration is not the identity of the particle.
These would be the identities, and these would be the electron configurations. That's right. And Joseph, to take it one more step, electron configuration alone will not necessarily tell you what the identity is. And Joseph probably either intentionally or inadvertently stumbled onto something really good. Unless I tell you, or someone tells you, that it would be a neutral atom, it would be hard to know what this is, because it could be any of these possibilities, and a lot of other ones too. Yeah.
So when we do this, are we going to use the charges like for oxygen -2 all the time?
You bet. That's right. It's all back to the nomenclature things once again, man. Those set charges are the ones we're going to see on these different things. Good. Yes.
For like which group for the electrons configuration has the G groups in there?
So 4Ds or 5Gs and stuff like that, those are variable charges, Eric, and those ones you'd have to have more information to figure out what it's doing. But what we can do is talk about, if you know what the charge is, how to find the electron configuration. And this goes back to what Rain just asked about a little second ago. Noble gas configurations are awesome for the main group elements, all right? So those are the A groups, the ones that we've spent time with. But the transition metals, as well as the lanthanides and actinides that Eric asked about, we need to look a little closer. Now remember that the official rule when making a cation, a positive charge, is remove NS electrons first, and then you go to the other ones. And this is really important when it comes to the transition metals. So iron makes iron plus 2 and iron plus 3. So to make iron plus 2, you'd have to remove 2 electrons. To make iron plus 3, you'd remove an additional electron. And notice here what's going on. So iron in its neutral configuration is an argon 4s2 3d6. And it might be tempting to remove these 2 electrons first from the 3d orbital, but that's not what happens. You take it from the highest end, and all of the transition metals and the lanthanides and the actinides have an s orbital first, all right? So what it means is that when you make a positive 2 iron or a positive 2 chromium or vanadium, the s electrons are always the first ones out. So iron plus 2, we remove 4s2, it's going to be argon 3d6. And after that, if you remove additional electrons, then they'll start coming from the 3ds. So this is a little bit strange and stuff, and it leads to some interesting properties of transition metals that you don't see with other kinds of pieces. So notice here and stuff that the 4s2 3d6 of iron becomes a just 3d6 configuration for iron plus 2. And if you make iron plus 3, then you'd start removing the electrons from there. So the transition metals, the lanthanides and the actinides, like Eric brought out, always take out those s electrons first, and then you start working on them. All the transition metals are exhibiting d electron behavior. That's why these guys are variable charge. They're pretty close in energy to it. Transition metals are a little weird. Another thing that becomes really important is the magnetism of the species that are done. And this is where it's really important to know where the electrons are coming from. Now, a diamagnetic system just means that in an orbital, every up arrow has a down arrow. Every spin up has a spin down associated with it. Zinc 2 plus comes from zinc. You remove the 4s electrons first. Zinc 2 plus is a 3d10. It's a diamagnetic ion. So every time we dealt with like zinc chloride or something like that, the zinc is diamagnetic and not interested in magnetic fields. However, you do get some crazy magnetism when it starts coming to the transition metals. Here's the iron 2 plus I showed just a second ago. Notice how it has 4 unpaired electrons, all right? So that's really paramagnetic. The most paramagnetic one on the first row of the transition metals anyway is a manganese plus 2, and it has 5 unpaired electrons. Now, the more unpaired electrons you have, the more magnetism power, if you will. So we would say that this is the most paramagnetic of all. This one is not magnetic at all, it's diamagnetic. The number of unpaired electrons influences how paramagnetic something is. All right, so here's an example of a problem you could see. It says, which of these ions corresponds to the following electron configuration? And there's 5 different choices and stuff that are available. So what I would do on a problem like this is, first of all, notice how the 4s electrons are empty. And if this is a 3d element, then you'll take the 4s out first and add 3d to it. So for example, earlier we saw iron plus 3. Iron plus 3, iron is number 26. It had a 4s2, 1, 2, 3, 4, 5, 6. It was a 4s2, 3d6. And to make an iron plus 2, the 4s electrons were removed. And then if you're making iron plus 3, the 3d6 becomes a 3d5. This is not a 3D5 configuration. This is a 3D7 configuration if you count up the number of arrows. So there's not enough electrons here to represent an iron plus 3. Why is rhodium not a possibility for this electron configuration?
Wrong row.
Wrong row, well done, that's right. Rhodium is a very cool metal. Rhodium's down here, all right? But rhodium is a 4D metal. So rhodium is in the wrong group to be part of this, all right? So we can kick rhodium out. Cobalt plus 2. Cobalt, scandium is 1, 2, 3, 4, 5, and then getting 6, 7. Cobalt is a 3D7 noble or transition metal. Cobalt plus 2 means you'd remove the 4s2. Cobalt here is a great possibility. Cobalt 2 plus has the 3D7. Calcium 2 plus is a noble gas lover, likes the noble gas. It's cool kids on the back of the bus. Removing 2 electrons from calcium makes it argon. And nickel, if you figure it out, has like 1 more.
So if it was like cobalt minus 2, would that mean you would add 2?
Yeah, that's right. So if it was cobalt minus 2, first of all, Avenir, these would be filled up here, it'd be 4s2, and you'd have then 3d9. That's right, well done. Avenir extended it to add electrons to it. They just go in the lowest unoccupied space.
I also wanted to ask, what groups again are the ones that minus the n? It's like n minus 1. Is it just the metals?
All of them go highest n first, and then you go n minus 1 after that. So even when we made phosphorus 3 plus from phosphorus, the highest n was the one you take out. You had a tie between 3s and 3p, so highest n plus l, but that's a universal rule. Anytime you take away electrons, it's highest n first, which means the 4s comes before 3d. And in that case, if you have a tie like 3s, 3p, then the 3p's would be the first ones out. Last one's in, first one's out for those. Good, but that's for all of them. Good question. Other questions? All right. The last thing I need to talk about is something that's kind of fun. Well, fun is a strange word to use this morning, but anyway, it's kind of helpful. It has a lot of imperfections to it, but it can be kind of useful, and it's what's called a periodic trend. And periodic trends are trends that you see on the periodic table. We've already seen, for example, that metals are on one side and non-metals are on the other side. And we've seen some of the charges that can come out of the periodic table, the fixed charges. There's another set of trends which can be helpful. And as in my world, these are really helpful because sometimes people will come at me from like Chem 104, all right, and they'll say, oh, well, which one of these atoms is bigger? And, you know, with me and my PhD, right, I should know all these things, right? Well, I don't know the sizes of any of the atoms. Like, I can guess that the atom's about an angstrom, but that's another whole story. But anyway, I really don't know off the top of my head, like Spock would. Star Trek reference, sorry. CJ, good, I'm so happy you're smiling. Like, Prophet, back on. I really don't know the sizes of any of the atoms. I don't, okay, it's my honest truth. But I can use these kind of silly periodic trends to make really good predictions as to which ones are bigger and smaller. And these are some of the hints I want to give to you. So if you're talking to someone in Chem 104 and they're like, oh, well, you're taking the big level of chemistry, you should know. No, of course you don't know, you can get on Google. But anyway, these periodic trends can be helpful, kind of spur of the moment. Always be a little suspicious of the answers you get from these. And I'll show you examples if I have time here where they'll be weird. There's a handout in your companion, the periodic trends handout, which can be really helpful. And all of these trends, we're going to look at 4 of them, all right? These trends are just things that kind of go from one direction to the other across the periodic table. All of these trends, quote unquote, are really about how the electrons are held in, all right? We talked about a long time, problem set 2, I think, how most of the volume of the atom is based on the electrons, all right? So the electrons are held tighter, it's going to get smaller, things are going to be different. On the other hand, if it's not held as tight, the atom will get bigger. So sizes and the energies to remove electrons, all of these things are really based around how the electrons are held together. On the periodic table, we're going to see, especially next quarter, how electrons are generally held a little tighter as you go left to right. So that's another interesting thing we'll talk about more later. On the other hand, as you go down the periodic table, you go from 1s to 2s, and 2s to 2p, et cetera, et cetera. So the atoms themselves get bigger. The electrons get further from the atom. So as you go down, the electrons are held not quite as tight because the atoms are getting bigger. On the other hand, as they go left to right, you're going to see they're held a little bit more tightly. So this is one interpretation of the periodic trends. And I'd like to give you my kind of cheesy version. And this is probably important enough I should shift the camera a little bit. So there's 4 trends we're going to look at. There's the size of atoms and ions. And the other one we're going to look at, electron affinity, and what's called the ionization energy. Now, my cheesy rectangles here are like the periodic table, all right? Hydrogen, upper left, helium, upper right, francium, basically down here, radon down there, all right? If anyone ever asks you anything about size, size gets bigger as you go left and down. So what that means by this periodic trend, if you are curious, let's pick some atoms. If aluminum or indium is bigger, okay, well, indium is more down than aluminum, all right? Indium should be a bigger atom. If someone wants to know if aluminum or silicon is bigger, left and down, remember the rule. So aluminum is more left than silicon. Aluminum would be bigger than silicon. But Dr. Russell, what if it's aluminum or germanium? Oh, good question, over us at the back. Sorry, my caffeine is kicking in. So aluminum is more left, germanium is more down. I promise I'm not going to ask you those kind of questions. If someone in Chem 104 asks you that question, usually the down is bigger than the left, but I'm not going to ask you those things. So left and down. So one of the biggest atoms is this francium down here in the lower left corner. It's really, really big. One of the smallest, of course, would be helium. So left and down can be the size of the atoms or sizes of the ions. Now, for electron affinity, it's the opposite. It's up and to the right, all right? So generally speaking, all right, as electron affinity and ionization energy, if you want to know which one has the bigger electron affinity, let's say sulfur versus chlorine. Chlorine is more right than sulfur. Chlorine should be bigger. Same thing up and right. So chlorine would be have more electron affinity than bromine, stuff like that. If you can understand my very, very cheesy thing here on the chalkboard, you've got this.
So when you say electron affinity, you mean more electronegative?
No, electron affinity and electronegativity are different. And electronegativity we'll use a lot next quarter. If electronegativity is like this one down here, it generally is up and to the right. But electron affinity is a little bit different. We'll talk about that later. Also right now, if you don't know what electron affinity is, ionization energy, honestly it's okay. I just want you to know, all right, that trends evolve. So that if someone asks you sulfur versus chlorine or potassium versus sodium, sizes left and down, that'll be the biggest atom, the biggest ion. Electron affinity, on the other hand, up and to the right. So the one that's closest up here to the upper right corner should have the largest one. So what I'm going to do in the time I have left is do some examples of how these things kind of relate. I'll also tell you some examples of how they don't work so well. So you should always be careful. If you have the time, get out your phone or whatever and put in the Google values. On the other hand, someone stops you in the middle of the class and wants to know, these can be really, really handy. So this is truly all my tricks are revealed here kind of thing. These are nice ways and stuff to figure out what's going on.
I know it's part off topic, but the lanthanides and the actinides, do we just imagine them somewhere in the middle? periodic table?
So, Joseph, that's a good question. The lanthanides and actinides are actually right here. All right. If you look on the far left-hand chalkboard, someone wrote this up there, and I haven't erased it. The lanthanides and actinides actually fall in between these, and that still works, Joseph. More than it doesn't. All right. So if you have to make a guess, if someone's asking you about, say, cerium versus neodymium, then cerium would be bigger. That kind of thing. Okay. All right. So they use effective nuclear charge to talk about why this happens. I'm not going to spend a lot of time with this because honestly I don't believe in it that much. But if you use effective nuclear charge, people figure out what's going on. I could care less. This and basically they think, here's what this is my favorite screen for what effective nuclear charge is. The nucleus is right in the middle. That's where all the protons are, all right? And what effective nuclear charge is all about is that sometimes the outer electrons are shielded a little bit by the inner electrons. Tiff, if she does anything, I'm right here in front of her. I'll know it. All right, Tiff, you better. All right. On the other hand, Savannah back there, she can be writing poetry and stuff, and I probably wouldn't know. She's further from me. So Tiff is shielding Savannah, kind of from my attention. This is kind of like what happens with the nucleus. All right. The nucleus and Tiff are going to be very closely related, very tight with each other. But Savannah then is going to have a little bit more room to kind of wander around and stuff. That's the idea of effective nuclear shielding. Like I said, I don't really believe in it totally, but that's a rationale that's used. Anyway, so you can approximate them, and if I had time, we talk about it, but we don't. There's a website with more information. But here's something that's kind of interesting. Now, these are actual relative energies of the elements on the third period. All right, so we're looking here at sodium through argon. And notice how these are supposed to be right. The 1s's are all getting lower, and the 3p's up here and stuff like that. So you do see an energy drop going left to right on the periodic table, and this is why they feel that the effective nuclear charge is useful. The important thing for us, though, especially since this is the last day of new information, is that your size is going to get bigger as you go left and down in the periodic table, all right? Especially if you go down. If you go down, you're going from a 2s to a 3s. We saw that as n gets bigger, the size gets bigger, so that's a big-time reason why that works pretty well. Size increases going right to left. So if you go left and down on the periodic table, you're going to see your sizes getting bigger. Here's some example values and stuff. Now what we see here, these are all group 1A metals. And the numbers right there, those are picometers, so it's a pretty small amount of values. But you can see here how they are getting bigger. So this 265 is bigger than 152, for example. All right, you can see then how this is the trend and stuff going. So going down the periodic table, the size thing works pretty well. 4s is bigger than 3s, et cetera, et cetera. Going right to left is another way to see that the atoms are getting bigger. This isn't as good. I'll show you here a little better thing in a little bit. But you can see that generally, chlorine is 99 on the far right picometers, and sodium over here is 186. So going right to left is one way that these sizes are going to get bigger. And again, this works fairly well on the periodic table. It works very well, I think, going down, up from top to bottom. It works fairly well going right to left. This is a table with a lot of values of the atoms. And I point this up here because I want you to see that these trends are not perfect. Now, generally, as you go right to left, these numbers are getting bigger, and these numbers are the sizes of the atoms. So you can see here already, fluorine, 71, is bigger than oxygen, 66. And you can see down here, for example, tellurium, 143, is bigger than antimony, 141. So if these trends were perfect, the numbers would get consistently larger going right to left. We use this particular section right here because it works out really well. All of these numbers are getting bigger as you go right to left. But you can see on these other ones, it's not necessarily the case. So these trends are trends, all right? They're not perfect. They're things to use when you don't have any other options available to you, and that's totally fine. But do realize that more than not, they work fairly well, but especially going right to left, sometimes you will see problems with it. So here's a typical kind of question you might see. Here's 4 atoms. Which of them is the biggest? Which one has the largest atomic radius? And again, for sizes of anything, sizes get bigger as you go left and down. So NA is right there. Of course, B, A, L, and C, I believe. Which one is most left and down? Sodium. That's right. It's most left and down on the periodic table. So again, there's no like magic to this, right? It's a little bit cheesy, like I said. It's not perfect, like I showed you just a second ago. But if you have to guess, more often than not, left and down is the way to find the biggest one. Any questions? Okay. Here's the trends in atomic size, and you can see there's like some little bumps once in a while and stuff, but it's all right. Joseph, here's some of the transition metals, and again, more often than not, these trends work for those guys as well. Again, it's not perfect or anything, but it's okay. Now, for ions, the positive and negative charges, it's interesting what happens. Remember that lithium has 3 electrons and 3 protons. And lithium, like all the group 1A metals, likes to be positive 1. It wants to lose an electron. Well, if you lose an electron, you now have 3 protons still, because lithium is lithium, lithium plus or lithium, but only 2 electrons. And notice the size is what happens. We went from 152 picometers, to 60 picometers. So if you make a positive charged ion, in a nutshell, the atom will be smaller, all right? And I like to use the idea here of protons being parents and electrons being the kids, all right? If you have 1 parent proton for every 1 electron kid, 1 parent's going to be able to watch that kid pretty well. And you know, if 1 parent has to go to the bathroom or something, then they can keep an eye on 2 of them and stuff like that. However, if you have 3 parents and 2 kids, those kids aren't going to be able to do anything. They'll be stuck on their phones, man. So anyway, 21st century. But anyway, the kids are going to be pretty under control because they have so many parents watching them. So the sizes, the amount of craziness the kids can get into diminishes a lot if you lose one of the electrons. In a nutshell, for chemistry, if you lose electrons, now you have more protons. The protons are going to pull those electrons in a little tighter. Cat ions, positively charged ions, always smaller than the atoms they came from. And I don't say always very much, but I will here. Cations are always smaller than the atoms that they came from. So sodium metal versus sodium plus will be smaller. Magnesium versus magnesium 2 plus, magnesium 2 plus will be smaller. All positive ions are smaller. But the opposite happens when you make an anion. So fluorine loves to make fluoride. Fluorine has 9 kids and 9 parents, 9 electrons and 9 protons. But fluoride has an extra electron, 10 electrons. Now, there's no way that those parents are going to be able to keep as much control over their electron kids. So the anions actually get bigger. The kids are more likely to get in trouble because there's not as many parents around. This is really cheesy, and I apologize, by the way, but bear with me, it's the last full lecture day. Anyway, so fluorine, fluoride is bigger than fluorine. It actually goes up by quite a bit, you can see. And here's another thing I'll say. Anions are always bigger than the neutral atoms they came from. So fluoride is bigger than fluorine. Oxide would be bigger than oxygen. Phosphide bigger than phosphorus. This works all the time across the periodic table. Anions are bigger, cations are smaller. So what this means then is that if you make a graph, and this is what people do sometimes, of ion sizes, first of all, these ion sizes are a little bit cheesy. You have to differentiate between the negative anions and the positive cations. Metals like to lose electrons, non-metals like to gain. However, if you use your imagination a little bit, going left and down, just like for the atom sizes, you're going to see things getting bigger. So for example, beryllium 2 plus is smaller than lithium plus. Aluminum 3 plus, smaller than magnesium. So notice left is getting bigger and down gets bigger too. But the one caveat is that you do have to separate the anions from the cations, all right? So like 146 is larger, but if you look at just the anions, then left and down works really well too. So what we've just looked at here is cations and anions. Positive ions and negative ions. Positive ions are smaller than the atoms they came from, and that's what these little pictures are right here. The purple part is the neutral atom, and the dotted line is the neutral atom, and the purple part is the cation. And all of them are shrinking, all right? Cations always smaller than the atoms. Anions are always bigger. So this dotted line now is the neutral atom, and the gold or green part there is the anionic part. The anions get bigger, and generally left and down is the way to find the sizes for them. Here's a possible question. Which of these should have the largest atomic radius? And this is kind of a cool set because we have argon, chloride, sulfide, and phosphide. They're all along the same row of the periodic table. And what that means, if you figure out the electrons, all of these have the same number of electrons, all right? They just have different number of proton parents. And the one that's going to get into the most trouble, if you will, is the one with the fewest number of protons relative to the number of electrons. And you can see there that phosphide, P minus 3, phosphide has 15 protons, because phosphorus always has 15 protons. But it also has 18 electrons. So those kid electrons are going to get in more trouble with that one than they will the other one. Another way to answer this question, left and down. Phosphorus is the most left of these elements. That would be another way to answer this question. Now, one thing that a lot of you probably thought, sure, in the back of your mind when you have a moment, is like, why is magnesium always +2? And why is sodium always +1? And oxygen -2? And we can start to figure out these kind of things by looking at the next periodic trend, which is ionization energy. And the ionization
To remove the outermost electron from a magnesium atom requires 738 kilojoules of energy per mole.
Ionization energy is the energy required to remove an electron from an atom, all right? And this 738 kilojoules number, that's the energy required to remove one electron from magnesium. Now we know that magnesium as a group 2A metal prefers to be +2. So let's figure out the energy for taking away one more electron. And you can see here how it's a little bit larger. We now have more proton parents than electrons, so it takes a little bit extra energy to take that out.
Removing the second electron requires more energy, 1,451 kilojoules per mole.
So if you add up these two energies together, which is like 2,200 something kilojoules, that's the energy required to take magnesium to magnesium +2. And that seems like a lot of energy, but that's actually a amount of energy which through heat processes and stuff you can regulate. But let's figure out the energy to remove a third electron. Let's figure out the energy to make magnesium 3+. Now we've never dealt with magnesium 3+ in here for a reason. Let's see why. Look at the energy difference to go with magnesium 3+.
To remove a third electron from magnesium requires much more energy, 7,733 kilojoules per mole.
It's almost 3 times the energy to remove a third electron than it is to remove the first two. And if you think about this as like a type of a currency, because energy is the currency of physical science, then it's almost like, 2,000-ish for these two, an extra, 6,000, 7,000 for that one. That's a high energy price to pay. So because the energy to remove that third electron is so great, that's why we never see a magnesium 3+. Going from magnesium to magnesium 2+, this energy is actually doable in the real world. But this extra energy to go like basically 3 times the amount is pretty tough. The oxidation number, or the charge on the metal then for the main groups, is usually equal to the group number, all right, because that's a good amount of energy to release. So ionization energy is where these numbers come in. You'll sometimes see things about first ionization energy or second ionization energy. That would be the energy to remove 1 electron or 2 electrons. You'll see weird graphs like this, all right? And what I'd like you to see more than anything is that more than not, these energies are getting bigger as you go up the groups, all right? So if you kind of do this kind of 3-dimensional thing, and generally they're getting bigger as you go right. Now right, you can see it's more like a stairs, and my right doesn't work quite as well as the up part. But if you have to make a guess as to how ionization energies go, again, up and to the right. So the up ones, hydrogen has a higher energy cost to remove an electron than lithium does. And lithium would be higher than sodium, stuff like that. So the Z star thing, which is effective nuclear charge, means that metals basically are good about giving up electrons, reducing agents, and nonmetals generally like to take the electrons from them. They don't give their electrons up quite as easily because they have the higher ionization energy. So the size, blah, 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 keep going there. All right, here's another problem you might see. If you needed to figure out which one of these has the largest first ionization energy, first of all, focused on largest, you want the biggest value, and ionization energy up and to the right. So of these same 4 atoms here, which one is most up and to the right on the periodic table? Carbon, that's right. Carbon is most up and to the right. Sodium, aluminum, boron, carbon. Sodium is most left and down. Carbon is most up and to the right. So you would guess carbon right here to be the answer. Here's the group 1A metals.
Lithium is the first of the group 1A metals. It reacts with water to form lithium plus 1 ions, losing an electron from a 2s orbital. Compared with sodium and potassium, lithium reacts rather slowly. Sodium is the second of the group 1A metals, occupying a position just below lithium on the periodic table. When it reacts with water, it loses an electron from its 3s orbital. The reaction of sodium with water is more vigorous than that of lithium. Potassium is the third metal in group 1A. Lower than both sodium and lithium on the periodic table, it is even more reactive with water. The valence electron lost by potassium upon reaction with water comes from a 4s orbital.
So if you look at these 3 metals, all right, they're getting more reactive, lithium, sodium, potassium, and that's the order on the periodic table, all right? Lithium's at the top, sodium's next, potassium's next. What would we predict about the reactivity of rubidium?
Lose one from the 5s orbital.
Good, more, I like all of these answers. I heard more reactive, I heard lose one from the 5s orbital, that's right. Reactivity will go generally get bigger and bigger as you go down the periodic table, which is kind of cool. This is just kind of for fun, but I had to show it to you.
20,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assets Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
Okay, so sodium and water is one of the classic like chemistry kind of demos and stuff because it can be really crazy how it works out. At the end of World War II, they had a lot of extra sodium metal around. And sodium metal is used for things like depth charges and stuff like that. So they needed to get rid of it because you don't want to have a lot of extra sodium around. So at the end of World War II, somewhere up in Washington, they dumped these huge barrels of pure sodium metal in, and you can see right? Sound effects not necessary, right? So wonderful pyrotechnics, absolutely. However, sodium metal and water make sodium hydroxide and hydrogen gas. The explosion comes from the hydrogen gas, but the problem I always have with this video is, oh, that poor lake, totally gonna be doused with sodium hydroxide, a base. Changing the amount of acid and base can affect the wildlife. They said there were no fish. Yeah, there's not gonna be any fish after that. But either way, where all water is related, right? It's part of the water cycle. So this is an interesting philosophical video. I'm glad they got rid of the wartime extra stuff. That's good. Having less war, good. But on the other hand, environmentally, I think there were some problems and stuff from that. So just realize things have changed over time, hopefully for the better. Anyway, electron affinity is the last trend. Electron affinity also increases up and to the right. And electron affinity is closely related to electronegativity. We'll use electronegativity a lot in Chem 222. Electron affinity is actually an energy that you can that's given off when anions form.
When a gaseous atom accepts an electron to become an anion, the energy it releases is a measure of its electron affinity. For chlorine, this is minus 349.0 kilojoules per mole.
So when chlorine becomes chloride, it's actually slightly exothermic. Energy is given off. And the electron affinity is that number they just said, and I apologize, I forgot. But some of the atoms on the periodic table like getting electrons so much that they release energy, all right? Taking away electrons for ionization energy always is going to be endothermic. But these kind of processes often are exothermic. You'll actually get energy out. This is especially helpful for the nonmetals. Nonmetals love to get the extra electrons. You can have first electron affinity and second electron affinity. This is going from oxygen to an oxygen -1. You get a -141 kilojoules. And anytime you see an exothermic reaction, those are reactions which are most likely to happen. So oxygen does like getting an electron. It likes to become oxygen -1. If you do things though like nitrogen, sometimes you'll see things of like 0 values, which is really weird. I don't think they quite understand why the electron affinity is 0 for nitrogen and it has a negative value for oxygen. But what you can do though is you can get these numbers, and these are just numbers and nothing you have to worry about. Now, the confusing part about these, all right, is that you have to realize that some of these up here are negative, exothermic, and some of them actually are kind of positive. But generally speaking, up and to the right, they get bigger. It doesn't work very well for a lot of my metals, as you can see, which is frustrating. On the other hand, if you start here with thallium at least, they get bigger going up, more or less. Actually, not very well. They get bigger going right. Notice that noble gases don't really apply here. Noble gases don't really like to gain or lose electrons. So you'd have to force electrons into them. And also, which is very weird and different than electronegativity, is that fluorine, I really feel, should be the highest one here, but chlorine is actually higher. So of all the periodic trends, I really dislike electron affinity the most because the trends are the least predictable, all right? Like generally up and to the right, it gets bigger, but man, there's a lot of problems with this. On the other hand, someone wants to know which one has the larger electron affinity, all right? Generally speaking, up and to the right is bigger. Here's some things. No one really understands why fluorine is less than chlorine, and we'll talk about this more in Chem 222. But it is, electron affinity is kind of nice because it rationalizes why ionic
The reaction of sodium and chlorine is governed by the arrangement of the electrons of each species about its nucleus. Chlorine is an oxidizing agent because it has a high electron affinity. Sodium is a reducing agent because it has a low ionization energy. The redox reaction produces the ionic compound sodium chloride, which contains one sodium ion and one chloride ion.
The energy that's given off is arguably the electron affinity energy and stuff, so. But anyway, they use this sometimes for rationalizing the formulas that we've spent a lot of times figuring out and stuff, so it's kind of cool. All right, so that's it for this section. On Wednesday, we'll start reviewing a little bit for the lecture. Again, some announcements. Remember that the exam 2 extra credit Wednesday at 1 o'clock is when it's due, no exception. And 2 lab, bring problem set 6, your lab notebook, and a printed copy of the hydrogen spectrum lab. Have a great day. Thanks, guys.